Unit 4 is about acids and bases, and I'm going to use several concepts that you learned about when you learned about acids and bases to design an extraction protocol to separate three molecules that are dissolved in chloroform. And as Megan Trainor says, it's all about that base. And we are going to choose a weak base and a strong base, and by putting the extraction protocol in the correct order and how we use those bases, I think we'll be able to separate selectively these three compounds and get them all isolated. It'll be no trouble. Let me show you the three molecules that we'll be working with. The three molecules we'll be working with are all soluble in chloroform. First one is a carboxylic acid. Specifically, it's benzoic acid. The next one will have a phenol group, okay, phenol or phenol, but also I'm going to put an amine. You should have an intuition which groups are acidic, which groups can give up a proton, and which groups are basic, which can accept a proton. Now, there are some molecules and some functional groups that are both, but in general, if you throw these things into, for instance, water, there are some functional groups that can grab a proton from water. There are other functional groups that will donate a proton to water. I did say we have three molecules. The third molecule is an amine again, okay, and we'll put an isopropyl group. All of these are soluble in chloroform. And the thing is, in lab, what if you're given a beaker of these three? CHCl3, chloroform. Okay. Not only are they soluble in chloroform, in the neutral form, they are not soluble in water. So in the neutral form, they are polar. You do have polar bonds, I should say, but they're not polar enough to be soluble in water. So in neutral form, they are not polar enough to be soluble in water. Okay. We are using an extraction technique. And as you recall, an extraction is you have a separatory funnel, a stopcock that can control the flow of liquid out this spout at the bottom. We're going to have two immiscible liquids. And let me make this one in red, maybe? Let me make this in blue. Hopefully you can tell the difference. That the resolution is good enough, or the colors difference is large enough. Blue on top, green on the bottom. We'll make it kind of checkered. Okay. Anyway, this bottom layer is chloroform, CHCl3, and it is called the organic phase. It's an organic solvent that separates from water. It is more dense than water. I'll discuss more about that in just a bit. This is water. Okay, they are immiscible. Now, I know in general chemistry, when you think about the dipoles, the bond dipoles, they don't totally cancel out, and you would predict that this molecule is polar. But again, this is not polar enough to be soluble in water. Actually, we're going to think of this as nonpolar. In practice, in organic chemistry, especially in the lab, things that are not soluble in water, you can consider nonpolar, or at least not polar enough to be soluble in water. And it's more dense. Chloroform is more dense. Now the water. I mentioned that we're going to be using some different bases, aqueous bases. But no matter what you dissolve in water, the density is not going to change that much. So whether that water is neutral acidic, or basic, the density still equals around 1.0 grams per milliliter. And chloroform will always be on the bottom. Now this is a little bit different because most organic solvents are less dense. Diethyl ether would be on top of water. What else would be on top of water? Cyclohexane will be on top of water. I think some of you have seen cyclohexane water extractions before. Let me put that in quotes. It's chlorinated solvents that are more dense. That's actually the exception. Chlorinated solvents, more dense than water, and it doesn't matter if that water is acidic, basic, or neutral. Okay. Now, before we go into the details of the types of water we're going to use, we are going to do some acidic water and some basic water. Let me give you a couple of quotes that should be rolling off your tongue when you talk about acid-base chemistry and extractions. The first one is like dissolves like. That means that if a molecule is polar enough, it will be dissolved in the polar solvent. But if it's not polar enough, or if it's it's nonpolar, it will be soluble in the organic phase. Now it's not going to be a complete separation. It's not going to be 100% into water and 0% into chloroform. It'll be some partitioning, maybe 95% to 5%. But molecules typically have a preference, whether they are soluble in organic solvents or aqueous solvents. At this point, we have a beaker. Okay, we have a beaker, and that beaker has chloroform, and all three of these are in the chloroform. All three of these are in the chloroform. So how do you separate that? Nothing is precipitating. They're all dissolved. Well, how about this? The next quote is charged organic molecules. It could be plus charged or minus charged. Charged organic molecules are usually soluble in water. Oh, if I can make any of those three charged, then I will transfer that molecule from the organic phase up into the aqueous phase. And I do want, the strategy is to get one by one molecules into the aqueous phase. All right. Let me put that charge for us, actually. The goal is to separate these three molecules ultimately, but the strategy is to get one molecule at a time into the aqueous phase. So goal, this is not a purpose, right? The purpose of the lab, this lab we're designing, is to separate three molecules using acid-base chemistry. But our first goal, or our the way to do that, is to transfer one molecule at a time. To the aqueous phase, the water phase. Okay, where's the acid-base chemistry coming into play? Let's take a look at the first molecule. The first molecule is carboxylic acid. Carboxylic acid. And we're going to use a common base, NaOH, plus NaOH, aqueous. Right now, this is chloroform soluble, CHCl3 soluble. Definitely not water soluble. Let me put a box here. We're going to put in the equilibrium arrow and decide whether it favors the right or the left in just a bit. Base, acidic proton. Therefore, your products are going to be the deprotonated acid. Okay. And what happens? The OH minus, you got to visualize this as separated, Na plus OH minus. The OH minus grabs the proton, the acidic proton, and it actually becomes water. Here we have a charged molecule. I don't know yet if I make a lot of this when I mix it with aqueous sodium hydroxide. What I do know is whatever is deprotonated will actually be more soluble in water, and we could write here H2O soluble. But more specifically, we should call it basic water, right? H2O soluble basic water because it's a base. That's one strategy to separate this to get into the aqueous phase if we make a lot of this deprotonated form. The next pink quotes you should know is equilibrium favors the blank acid. Stronger or weaker? The answer is weaker. What? Why? Because if you're a very strong acid, you want to give up that proton and get to the product side or the other side of the reaction. But if you're a weak acid, then you don't have a lot of motivation to get rid of that proton. So you could think of this as the reaction goes away from the stronger acid, or you could think of it as the reaction deprotonates the stronger acid. But most people say equilibrium favors the weaker acid. Let's look at the pKa's. The acid on the left side is the carboxylic acid. We need the pKa of this carboxylic acid. The acid on the right side is that. This is the conjugate acid of the base. So this is the pKa we want, the pKa of water. Okay. And we're going to find out which one's weaker. Draw our equilibrium arrow. The pKa table that a lot of people use is called the Evans pKa table. You could Google it, Evans pKa table. And the benzoic acid, there's a carboxylic acid group here, but the benzene part is right here, C6H5, so that's the X. So that is 4.2. Water is, you could almost think of it as an alcohol because of the OH group, is 15.7. And it's also here on the inorganic side, 15.7. I lost the number. 4.2, 15.7. 4.2, 15.7. 4.2, 15.7. Okay. Which is a weaker acid? This is a weaker acid. That means we get a lot of this. We get the equilibrium going to the right-hand side. Okay? And we get most of this. Great. We're able to get this out of the organic phase and into the water phase. But there's an issue. The issue is this molecule right here. Now, again, my goal really is to get one of these molecules into the aqueous phase, okay, and separate that out, and then do another extraction to get a second molecule into a new aqueous phase. But if I use sodium hydroxide, I will actually deprotonate this as well, because, why? The pK of this, and I'll write it here, that's a phenol, okay, that's a phenol. If we look at the Evans pKa table, nope, right here, phenol is an alcohol, but it's a special type of alcohol. Most alcohols are around 15, 16. But look at this. This is your benzene ring with an OH. It's 9.95 or 10.0. The pKa drops. It becomes more acidic than a normal alcohol. That's because, I won't go over it here, because of resonance of the anion, the conjugate base. But the number I wanted is 10.0, and it's here. Okay. The thing is, if you mentally put this molecule down here, you have 10.0 versus 15.7, and you will still get mostly deprotonated form. So now that molecule is soluble in basic water as well. So we did not do what we wanted to, which is only transfer one of these molecules. Now, as an aside, you may wonder, what about this group here? Isn't that acidic? It's acidic, meaning that you could remove the proton, but the pKa is super high. the pKa equals 36. So when you mix this molecule with some acid, more likely the acid is going to grab, when you mix this molecule with some base, the base is more likely to grab this acidic proton, not this acidic proton. Okay. Actually, this is basic. We could get this charged by adding hydrochloric acid, and we're going to do that in just a bit. But there's a dilemma, right? The dilemma is I don't want to transfer both of these into the water. I only want to transfer one of them. It's all about that base. If I use a weaker base, okay, think about this. The pKa of this equals 4.2. If I use a weaker base, I can probably still deprotonate the strong acid, but maybe not the less strong acid if I use a weaker base. Let me show you that base that I have in mind. Okay. So far, we have that one chemical reaction, right? The carboxylic acid with sodium hydroxide. The base I have in mind is nachos. What is that? That's sodium bicarbonate. And, oh, how about this? Let's look at that second molecule. Because I actually did not want this weaker acid to be transferred. Okay, I don't want to deprotonate this. But I still want to use a base to deprotonate the carboxylic acid. Nachos, NaHCO3. Okay. I did not come up with that name. Some undergraduate 10, 15 years ago came up to me and asked if I had more nachos, and I had no idea what they were talking about. They were talking about this aqueous solution of sodium bicarbonate. And it's unfortunately that name has stuck in my head. Well, first of all, to get the equilibrium arrow, we got to figure out what the products are. This group is basic, so it's not going to be deprotonated by this base. So that stays the same. And I have this. Okay. But look at my conjugate acid. My conjugate acid actually now is not water, but when this base, remember, you got to think of it this way. You have HCO3 minus separated from Na plus. Whenever you have a counterion, a metal, separate it because that's the actual base. You add another proton to that, you get H2CO3. I already told you, and we saw it in the Evans pKa table, that this phenol has a pKa around 10. But now I need to know the pKa of this H2CO3. Let me show you that. That I don't think is on the Evans pKa table. So I have another table ready for us that has mostly inorganic acids. And the way we read is I'm looking for an acid, HA, and I'm going to get the pKa, this last column here. H2CO3 is right there, carbonic acid. Carbonic acid, the pKa is 6.37. 6.37, 6.37. Oh, look which is the weaker acid. The weaker acid is phenol. So we have this, we have that. Now you may wonder, what? Why? We didn't do anything because this is not going to be deprotonated a lot because the equilibrium goes to the left. Why is that good? It's good because now when I do an extraction with nachos, look at this molecule here, the carboxylic acid. That's a pKa equal to, what did I say, 4.2. 4.2. If I use NaHCO3, sodium bicarbonate, and I have this, again, my product would be the deprotonated carboxylic acid. Okay, plus carbonic acid, H2CO3. I know this is a lot, okay? But to understand acid and base, you got to go slow at first because the numbers can, get all jumbled in your head. Heck, these pink phrases, you could get totally turned around. Charged molecules are usually soluble in water, or equilibrium favors the weaker acid. Okay? Because look what I have here. Look at this situation. I use the same sodium bicarbonate solution in that mixture, and I'm able to get this one into water, but not this one. See, this is the weaker acid. Equilibrium favors the weaker acid. So now I have this as the predominant form of the benzoic acid. This dude still stays in chloroform, CHCl3. This one is now in basic water, but more specifically, NaHCO3 basic water, and it's soluble. Think about your separatory funnel. If I do sodium bicarbonate, I could get this molecule, right, to go into the water layer, but not this molecule, not the second molecule. And we proved it right here. Okay. What about, fine, I'm able to do that. I extract with sodium bicarbonate and I get this into the water layer and not these two. How do I separate these two now? Okay. So we could now use the stronger base, right, and to get this into the water layer. All right. The point is, this molecule will never go into the water layer when you use a basic aqueous solution because this will never be deprotonated by any of those two bases. It can be protonated with HCl, okay, and we could do it that way. So we have several options. I like the idea that we use nachos to get rid of this, and then we have two options. We could use sodium hydroxide to get this into the water layer. Actually, that's our only option. Because if I use HCl, I will actually protonate this one also. So if I use HCl, I'll protonate these two amines, and both of them will go into the water layer. Man, let's say we have these two left, and I'm going to try this to make it a little more clear because it's actually something I would have tried and realized later that it's not working. Let's say these two are left. If I use now HCl aqueous, I know this looks a little strange. I'm trying to do two reactions at the same time. Now this is acidic. This is acidic. So now we have to find the basic groups, and it's some amine. But how do I know that? This is very acidic. This is very acidic. So this is going to be the acid. This group here is actually more basic. And you could actually use that as a general rule. Amines are more basic than alcohols. Because of that, we have these two molecules. And this one. They're both charged. And why is that a problem? It's because now both of these will go into the water. Both of them are HCl aqueous, soluble. They're both in the water phase. Now the thing is, what about the equilibrium? I forgot to talk about that. The equilibrium here, our conjugate base is Cl minus, right, for both of these. So what are the two acids? The two acids are these. We have oh, here, this is the first acid. Let's find the pK of HCl. This is going to be easy. It's such a strong acid that it's going to push. Oh, yeah, it's, what are they saying here? The pK is less than 1. Okay, we'll go with that. Let me see what Evans says, actually. Let's use Evans. pK is -8. pK can be negative. That's super acidic. Okay, this is the acid, and the pKa equals -8. These amino groups, these protonated amines, they have a pKa. Let me prove it to you. They have a pKa of around 10 to 9, and I hope I can find one. There's the amines, but we need the protonated amines. Look at these protonated amines. See, these are NH3 plus, NH2 plus. These are the nitrogens that are positively charged. We're going to let's pick up 10, 10.6. We have an ethyl with a NH3 group, 10.6. It's basically the same. We have an organic molecule with an NH3 group. We said this was 10.6. So the acid here is 10.6. And this one also, 10.6. Which is a weaker acid, -8 or 10.6? 10.6. 10.6 is weaker than 8, -8. 10.6 is weaker than -8. We should not, the point is, we should not use acidic water because these two will always go together. They will both become water soluble. I know that was a lot, and we haven't even yet put anything into the separatory funnel. Sorry, guys and girls. This is part 1. But trust me, if you understand the chemistry and the way that we're choosing equilibrium and the way that we get a molecule from organic soluble to water soluble, part 2 is going to be a breeze. Okay, so right now, the reactions that we are going to focus on is this one, NaHCO3, to get the carboxylic acid into the water. Okay, and then we're going to not use HCl. Instead, we are going to use what? We are going to use NaOH. Because NaOH will deprotonate that alcohol, the phenol, but do nothing here. This is not acidic, even with a strong base. So now we could get this to look like this. And when we do the pKa analysis, definitely, well, the pKa analysis, you have water, right? What was this, 15.7 versus this one, which is 10.0. Okay, so this is the weaker acid. And we get this to go into the NaOH aqueous phase. Okay. Stick with me. I promise that on part 2, we're going to start drawing separatory funnels and we will start pointing where each of these 3 molecules reside after we wash with either a strongly basic sodium hydroxide solution or a weakly basic sodium bicarbonate solution. Okay, come see me, part 2, please.